Hello, welcome back to AE 3530, System Dynamics and Vibrations. In this lecture, we're going to have a rather short lecture. We only have 2 pages left in this chapter, and we're going to cover damped vibration absorbers. So in this case, we're now considering a machine that has a dynamic vibration absorber installed with it that now has both stiffness and damping. I just circled the damping on the screen. So we now want to understand the effect of damping on the 2 resonant peaks that are introduced by the vibration absorber. Before we said we go from 1 resonance peak to suddenly 2 resonant peaks, and both of them without damping are infinite. So in this case, we're now going to look at how we can reduce those amplitudes by adding damping to the absorber. So we have here m1 x1 double dot plus, that's our equation of motion, plus c2 x1 dot minus x2 dot plus k1 x1 plus k2 times x1 minus x2. This is equal to our force F0 sine omega t. And then our second equation of motion is m2 x double dot 2 x2 double dot plus c2 x2 dot minus x1 dot plus k2 times x2 minus x1 equal to 0. From here, we're going to complexify and assume a solution of xi of t equal to big Xi e to the j omega t. Here for I equals 1, 2. And then from there we can go and compute steady state solutions, which I've gone and done below already. I'm taking this from the book that I was reading for this. And you can see that these are now complex. We have complex here. In this case, here, I guess this I right here, this kind of conflicts, but this I here is the square root of minus 1. Same with this I here, square root of minus 1. Same thing over here, square root minus 1. Here, square root minus 1. That's my mistake for having I as an index. We often use either J or I for imaginary number, and this particular book where I took this from happened to use I, whereas in the rest of our notes we've been using J. All right, in order to study this, we need to define a bunch of ratios. First, the mass ratio. This is absorber mass over the main mass. The static deflection of the system. That's what this delta is. The square of the natural frequency of the absorber. The square of the natural frequency of the main mass or the machine. The ratio of their natural frequencies. The forced frequency ratio, which is the ratio of the frequency of the forcing to the frequency of the main mass. What's known as the critical damping constant. And the damping ratio. And then we can express the magnitudes of x1 and x2 as the following here. We had to go through all of this in order to come up with some generalized expression that then allows us to make a single plot that represents and captures all of the different cases. So we go ahead and we plot the absolute values or the magnitudes of these, and we'll find here the following. So first, we have when zeta is equal to 0, we get 2 resonant peaks. That is represented by this dashed line that I'm going to highlight with the laser pointer over here as well. We get these 2 infinite resonant peaks. When zeta goes to infinity, we go back to our original system. If zeta is infinity, then the absorber cannot move at all because it encounters an infinite force. This is equivalent to having it be rigidly attached. And as a result, it will just shift the resonant frequency down. It shifts the resonant frequency down of the primary system because by having a rigid connection, it's like equivalent to just adding mass to the structure. If you add mass, then the square root of k over m gets smaller, so the natural frequency gets smaller. And then when zeta is not equal to 1, in this solid line, which I'll highlight now, this solid line here, we get these smaller peaks. But one interesting thing is that all of these curves intersect at the points A and B, regardless of the value of damping. You can go and you can find points A and B by substituting in zeta equals 0 and zeta equals infinity into equation 59. Equation 59 is up here. We can sub that in, and this yields the following equation. And we get two roots from this, and they indicate the values of the frequency ratios GA, which is omega A over omega, and GB, which is omega B over omega, where omega A is the frequency where point A occurs, omega B is the frequency where point B occurs. Okay. So the ordinates of A and B, that's their vertical points, these points here. These ordinates can be found by substituting GA and GB into equation 59. And then it turns out that the most efficient absorber is the one where the ordinates of A and B are equal. And this is called a tuned mass damper. And on the left here, I'm showing the response for a tuned mass damper. And here what we find is that we are able to minimize the amplitude of these two new resonant peaks that we've introduced by adding in the damping to the system, to the absorber. Okay, so this concludes everything in chapter 3 for MDOF vibrations. We've covered a lot in this chapter. In terms of what you'd be expected to do on an exam, you're absolutely going to be expected to find natural frequencies and mode shapes. You probably won't be asked to mass orthonormalize, and since we won't ask you to mass orthonormalize, you would need to be able to explain the process of how you would produce a final solution. Now, something on the final, we may ask you to mass orthonormalize. We may not. It kind of depends on what we're thinking about. But certainly, you should definitely know your process. You should know the entire procedure for solving these equations. We're not going to cover, or you're not going to be asked to solve for a vibration absorber type problem. This is really more for your knowledge so that you know these exist. But absolutely, you need to know how to deal with frequency response functions, how to deal with things like, absolutely natural frequencies, mode shapes, and modal analysis in general, and then also frequency response, what a resonance is, what an anti-resonance is, etc., things like that. All right, and that also being said, there's no classwork with this. For the rest of your time that you have available, I suggest you work on the homework on MDOF systems if you have not already started it.